Okay, the fundamental theorem of calculus says this. We're going to use a capital F for something different than a little f. And capital F basically just means that it's the integral. Notice the upper bound is a x, that's a variable, and the lower bound is a constant, a. The constant is basically not going to matter what it is here. So this is defined as the uppercase, okay? And it says the derivative of the uppercase function equals the derivative of the integral. And essentially what this is saying in a little more simple terms is the derivative of the integral is the function, or the integral of the derivative. Sometimes we introduce that plus c for the constant. You might have to know that information, but otherwise it's about the same. The really important part of, and most useful part, is the second part of this theorem, which tells us how to do an integral. So keep in mind that this is the integrated function, capital F. So I take my antiderivative, and we'll have this coming up uh, tomorrow, how to do the antiderivatives. But the definite integral with bounds a and b is equal to the function f of b minus f of a. So I do the antiderivative, I plug in b, and then I subtract. I plug in b and a, and I subtract them. Okay, that is the really, really important part of the fundamental theorem of calculus. This is what we're going to be using a lot. Okay, the last thing we're going to do is talk about the trapezoid rule. And the trapezoid rule is basically, instead of putting rectangles in my spot, so here's my function, random as it looks. Instead of putting rectangles in, I put trapezoids. Or in a few cases, these are triangles, but that's just a trapezoid with a side of 0. Okay, so that's the idea of this. The key is the area of a trapezoid formula. So this is my formula. Area equals 1/2 B1 plus B2 over H. So that means two bases. Now, here's the little trick to this, though. Initially, I have B1, B2 for my first trapezoid. My second trapezoid has B1, B2. My third trapezoid, B1, B2. If you'll notice that all of these inside ones are repeated. Okay? So we have a shortcut for the trapezoid rule. This 1/2 and this h are going to get combined into h over 2 because that's the same. And we're taking all of the y coordinates. Let's pretend we're just doing the bottom here. And we're doubling all the ones on the inside. Oops. And adding the outside ends. So I've made my chart before of all the values, and I didn't I didn't include both endpoints. I only used one of the endpoints. Well, with the trapezoid rule, you use both. The other way to look at it is the LRAM plus the RRAM divided by 2. And if you actually think about all the things that are in the LRAM, it's one of each of all of these to this n minus 1 point. The RRAM starts at the y1 and then goes to that. So I duplicate this whole middle section, which is why there's the 2. Okay. But that's the important thing. You duplicate this whole middle section. So there's a 2 on all. So that's kind of the trapezoid rule. Let's apply the trapezoid rule. The trapezoid rule is a better approximation than LRAM or RRAM. It's sometimes better than the MRAM. Not always. So here we're going to do 1, the 2. We're going to approximate this with the trapezoid rule with n equals 4. So that means I've got x values of 1, 5/4, 3/2, 9, nope, 7/4, and 2. I'm just going to give these all with a common denominator. That's 1 or 4/4. 5/4 is 25/16. Sorry, 4/4 is going to be 16/16. 3/2 we're going to do is 6/4, so that's 36/16. 7/4 is 49/16. And 2 is 4, so that's 64/16. To now use the trapezoid rule, I do h. H is 1/4. 1/4 over 2 is 1/8. So h is the width of each one of these boxes. If each one is 1/4, I do h over 2 is 1/8. Two times 25/16 plus 2 times 36/16 plus 2 times 49/16 plus 64/16. Again, I double all the middle ones. So I'm just going to write the numerators here. $72 and 98 is 170, and 64 is 234, and 50 is 284, and 16 is 300. I'm going to start trying to reduce a little bit. I can take a 2 out of that. Oops, that's an 8. That's 150. I can still take a 2 out, 75. I can't reduce 75 over 4. So I get 75 over 32 for my area. Okay, that is a trapezoid rule. Now I'm going to show you the real use of a trapezoid rule. So we're finding the average temperatures. And we have this chart. It starts at noon. Goes noon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and midnight. And the temperature at each of these times is listed here. And I'm told to average these. Because the gaps are not even, my average temperature is not simply adding them up and dividing by 13. Okay, this is more function-like where this dropped here from 7 to 8 more than it did from 8 to 9. Okay, so my average temperature over the interval would be given by the average value of the function, because this is some sort of the temperature function is something like this. It's not even, it's not smooth. So we know average value of a function equals 1 over b minus a times the integral from a to b of f of x dx. Well, I don't know how to find that integral, but I can approximate it with the product rule. I'm going to call this 0 and 12. 1 over 12 minus 0 times the not product rule, the trapezoid rule. Each one of those is 1, so h over 2 is 1/2. Now I'm going to double all the insides. What I have. Excellent. I'm recording a video right now. I'll get it recorded in a second. Xander, just leave it here. And so I've doubled all the middle ones. I do not double the ends. The trapezoid rule gives me 782. When I multiply it by the 1/12 here, I get 65.17 degrees for my average temperature. Okay? That is the trapezoid rule. An actually better approximation than the trapezoid rule. This is probably the best approximation, and I can't really tell you why it works, but this is called Simpson's rule. The number of subintervals must be even. This is a big, important clause.
That was started last night, and this was Mark, wasn't even game.
Curtis, I'm recording. It's okay. So, The Simpsons approximation. Instead of h over 2, it's h over 3. It looks a lot like the trapezoid rule on the ends, but inside, you alternate these twos and fours. Your next to the outsides must be 4. Okay, so we'll do one of these. And we're going to do 4 subintervals. So n is even, so we're good. So that means 4 subintervals is x equals 0, 1/2, 1, 3/2, 2. So that's 4 subintervals gives me 5 points. And you get an extra end. This is 0. 1/2 to the fourth is 1/16. That's 5/16. 1 to the fourth is 1. Times 5 is 5. 3/2 to the fourth is 81/16. 81 times 5 is 405. 2 to the fourth is 16 times 5 is 80. So, using Simpson's rule here, h is 1/2. 1/2 over 3 is 1/6. I can think of 1/2 over 3 as 1/2 times 1/3 because I multiply by the reciprocal. And then I start with my endpoint. My next one gets 4. Now I'm plus 2 times the one after that, plus 4 times the one after this. If I wasn't to the endpoint, it'd be a 2, then a 4, then a 2, then a 4, but I am to the endpoint. So I multiply this all out and I get 385 twelfths. And I will just tell you that that is the best approximation method that is out there. Okay, that's Simpson's rule. That's the end of 5.4, 5.5.